I want to introduce our next speaker. That's Professor Isabel Revilla. She's from the University of Salamanca, Spain, where she is active in the field of science and chemistry. Isabel produced close to 100 publications about her work. She will give an overview of the spectroscopy based approaches from the laboratory to the use of portables in MEAT research from the perspective of academia. Really nice subject, Isabel. Please, the floor is yours.
Thank you very much. So, good afternoon. I would like to thank the organizing committee for the kind invitation to present the work our group has been doing on the feasibility of use in the spectroscopy, the near-infrared spectroscopy, for prediction, decomposition, and for discrimination purposes. Here, I'm going to present some of the results that we have obtained on MEAT and MEAT product. Taking into account the title, Taking Spectroscopy from the Laboratory to Beyond, I'm going to start by a brief presentation of what a spectroscopy is. A spectroscopy can be defined as the investigation and measurement of the spectra produced by the interaction of electromagnetic radiation with the matter, resulting in absorption or emission. Electromagnetic radiation consists in an electric and a magnetic field that are perpendicular to each other. This electromagnetic radiation can have very different wavelengths, ranging from radio waves to the cosmic rays. In this presentation, I'm going to focus on the near-infrared spectroscopy that ranges from 800 to 2,500 nanometers. This technique has increased its relevance due to these advantages, such as being sensitive, fast, non-destructive, multiparametric, and with an easy preparation of the sample. So the second element of our spectroscopy is the sample. If the sample was if the bounds of the sample were ideal or an harmonic oscillator to observe the absorption of near-infrared radiation by matter, the energy must be sufficient because the energy levels are quantized. In this to observe transitions, the quantum number should vary just one unit. In this case, the molecular vibration will show only a peak in the spectrum. However, the bonds are not ideal, so they behave as an harmonic oscillator, and more transitions are allowed, such as +2 or +3 that are called overtones. In this case, a broad band is observed in the spectrum. In addition to matter radiation coupling, it's necessary to observe a net change in the dipolar moment. The higher the change in the dipolar moment and the higher the bond anharmonicity, the higher the intensity of the response in the spectra and the higher the frequency. Because of that, the bonds that involve hydrogen show the higher intensity and the higher frequencies that are observed in the near-infrared part of the spectrum. Other bonds that also show very high intense response in the near-infrared spectroscopy involve hydrogen oxygen or hydrogen phosphorus or hydrogen nitrogen. In this case, these bonds also show different absorption bands at different wavelengths. As a result, we have a spectrum that shows a combination first overtone, second overtone, and third overtone bands. When a monochromatic radiation interacts with matter, part of the radiation is absorbed, a part is transmitted, another part is reflected. Both showing a specular reflection and a diffuse reflection. This diffuse reflection occurs in all the directions and depends on the composition of the sample and also on the physical properties of the sample, such as particle size, shape, or compactation. This diffuse reflectance is the most important for near-infrared spectroscopy. According to Kubelka-Munck law, the relative reflectance depends on the concentration of the analyte. In this case, the relative reflection that is reflectance, sorry, that is defined as the reflectance of the sample divided by the reflectance of a standard. In this case, as I was telling, the observance that is defined as the logarithm of the inverse of the reflectance depends on the composition of the sample and on the physical properties of the sample. And because of that, each sample shows a very characteristic spectrum that can be considered as a fingerprint of the sample. The near-infrared spectroscopy started in the laboratory using benchtop equipment similar to those shown in the slide. The main parts of these equipments are a source, usually a tungsten halogen lamp, and an holographic grating that divides or scatters the light into individual wavelengths, a filter that removes the unsuitable lines, a reference that can be could be composed of different materials depending on the equipment, and another detector that is seated at 45 degrees to avoid the specular reflectance. In some cases, these equipments are coupled to a fiber optic probe that ends in a quartz lamp, in a quartz window that can be seated on the surface of the sample without any other preparation. Finally, we will have a spectrum. This spectrum can be used for quantitative purposes, such as the prediction of basic composition, technological properties, color, texture, fatty acids, minerals, or sensory properties. This spectrum can also be used for qualitative purposes, such as differentiation between frozen or unfrozen meat, to distinguish among species, among breeds or genotypes, among ages of the animal, diet, meat grades, or quality levels. However, as we saw previously, the bands are very broad and it's very difficult to correlate a specific wavelength with a specific molecular absorption. Because of that, it's necessary to use several chemometrics. Some of them are shown in the slide, such as PLAs, MPLAs, artificial neural networks, principal component analysis, and others. For quantitative application, to calibrate some of the compounds that are in our sample, the most usual is to use the modified partial least square. This process consists or implies to do a good sampling procedure, to perform the reference analysis, and afterwards to record the spectra of the samples. This spectra can be submitted to different spectral pretreatments, such as mathematical pretreatments shown in the slide. Among them, multiplicative scattering correction tries to avoid the effect of scattering avoid that this scattering effect is higher or more important than the effect of the chemical composition. The standard normal variate also tries to avoid the effect of a scattering process and show very similar results that multiplicative scattering correction. The trend mathematical treatment tried to avoid, to minimize, the baseline curvature and to avoid the effect of the particle size. Together with these mathematical pretreatments, several derivatives and smoothing can be applied. In this case, The degree of the derivative is shown in the first digit of this combination of digits. And the second, the third, and the fourth digit shows the number of points where the derivative, the first smoothing or the second smoothing, is applied. The first derivative corrects the shift in the baseline, and the second derivative corrects the changes in the slope of the spectra. In fact, for analytical purposes, a combination of all these treatments should be tested in order to find the best combination depending on the type of the product that we are analyzing and the type of the compound or the property we want to predict. In this case, for the prediction of hardness in the dry sausages, we use a multiplicative scatter correction with any derivative. Without any derivative. For the prediction of acid odor, we use the trend with a first derivative, and for prediction of juiciness, we use a standard normal deviation with a second derivative. After the spectral pretreatments, it's necessary to apply or to perform the principal component analysis, which aims to give information about the structure of the data and to reduce the variables, keeping all the information. After the principal component analysis, the spectrum is defined by a point in the new subspace, and the distance between the center and the point is defined as Mahalanobis distance. Each sample that has a Mahalanobis distance greater than 3 are removed from the dataset due to spectral reasons. Afterwards, a cross-validation is carried out. To do that, the original set of data are divided into different subsets. One of these subsets is used to check the goodness of the method, and the others are used to predict the variable. This process is repeated as many times as subgroups are formed. After this process, the standard error of cross-validation is calculated, and the samples that show a very high residual are removed from the dataset due to the chemical reason. I mean, the data that shows a t-value higher than 2.5. Finally, we have a calibration statistic of several calibration, and we choose the best calibration, taking into account that they show the higher value of RSQ, the lowest value of standard error or calibration and standard error of cross-validation, and the wider range of applicability. In this example that we use NIR for calibration of fatty acids and a stable carbon isotope in Iberian pig subcutaneous fat, we can see that it was possible to predict 14 fatty acids and 5 groups of fatty acids, showing RSQ values higher than 0.7. And in some cases, we find RSQ values higher than 0.9. After the calibration, it's necessary to carry out an internal validation. To do that, the predicted values of all the samples used for calibration purposes are compared with the references data, and a new RSQ is calculated together with a standard error of prediction and the standard error of prediction corrected by the bias. If we represent the reference by predicted data, we have this kind of graphic that shows that the goodness of the validation. We can see here that the RSQ of internal validation that is high, but not as higher as in the calibration step, and the standard error of prediction that should be as closer as possible as the standard error of prediction corrected by the bias. Finally, the external validation is carried out. In our case, in this case, a new set of data that has not been used for calibration purposes the property of these samples are predicted using the calibration curves, and the values compared with the reference values. And the test of student is calculated. And if the p-value is higher than 2.25, that means that there is no significant differences between the predicted and the reference value. However, there are some cases where the modified partial least squares do not perform as well. For example, in this case, only 10 out 20 parameters could be predicted, and the RSQ values were not very high. In this case, we tried with another chemometric tool, such as artificial neural networks. Artificial neural networks use the input data and through different algorithms predict the data, in this case, the sensory values of the samples. And the artificial neural network, the neurons are connected by artificial synapses that are weights given to the input data that stores the information acquired by the neural network, and that are optimized through the learning process. In our studies, we use a multi-layer perceptron neural network that is composed by an input layer that has as many neurons as input data, a hidden layer that has a variable number of neurons that should be optimized during the optimization process, and algorithm that has been chosen depending on the type of the problem. In this case, we use an hyperbolic tangent sigmoid algorithm. And finally, an output layer with only one neuron that use a transfer algorithm that also has to be optimized. In this case, we use a linear transfer. To optimize the artificial neural network, the initial data set is divided into 3 subsets: a training set that is used to calculate the weights that is going to associate with the input data, and to calculate the predicted data. This predicted data is compared with the reference data, and an adjustment of the weights has to be performed. The best neural network is that shows the higher value or R square. The other 50% of the samples are used to validate the neural network and to avoid the overfitting. Finally, 15% of the samples are used to check the goodness of the artificial neural network. To perform the calibration, multiple tests are done using different number of neurons in the hidden layer, and using different numbers in the seeds as the seeds values. After the optimization, we finally get a calibration curve for all the sensory parameters with values higher than 0.7, and in some cases, such in hardness, 0.9. Regarding internal validation, we can see that the artificial neural network showed higher values of RSQ than MPLS, and lower values of standard error of prediction. Regarding bibliography, we can see that it's possible to use near-infrared spectroscopy for several different quantitative applications, such as prediction of protein, intramuscular fat, or moisture. In fact, the good results has led this technique to be a reference method. However, for other compounds such as ash or collagen, the results are not as good as and depends on the work on the article tested. Regarding technological properties, in general, the results are not so good as for the composition, and the worst and the best values are very variable. Regarding the prediction of fatty acid composition of the samples, the results are quite good in the fat, but not so good in the meat. And finally, regarding sensory properties on fresh meat, only some good results on tenderness are reported. Finally, the last article showed that it was possible to predict only iron, phosphorus, and lead on meat samples. As I told before, near-infrared spectroscopy can be used also for qualitative application. I'm going to show an example of different chemometric tools that can be used depending on the problem. In this case, we wanted to differentiate between samples belonging to a protected geographical indication and other samples that were made or elaborated in the same region, but not on the but they don't belong to a protected geographical indication. As we can see, the principal component analysis don't show a very good separation among between the samples. So we tested the orthogonal partial least square discriminant analysis, and it performs quite good or quite well for calibration, but not in the validation subset of samples. For the reason, we try with the RMSX residual algorithm that it's included in the WinISE software of FOSS. And after the mathematical pretreatment optimization, it was possible to classify correctly the 100% of samples not belonging to protected geographical indication, but only the 84% of the samples belonging to protected geographical indication. Because of that, we tried with artificial neural network, and we tested several algorithms. As we can see, the algorithms related with a scaled conjugate gradient show best performance that the gradient descent. However, the Levenberg-Marquardt algorithm showed the best results and correctly classified the 100% of the samples. As I said at the beginning, the title of the presentation was From the Laboratory to Beyond. And what's the current trend in this area? Nowadays, the technology is moving forward to more to smaller and smaller equipment. This can be possible because of the advances in microtechnologies, such as microelectrical mechanical system, micro-optomet electromechanical system, or linear variable filters. Here we can see some of these devices available in the market. If we compare these devices, we can see that, for example, SIO shows a very narrow spectral range and with a low spectral resolution. In fact, this device was the first device advised as portable and very affordable. However, the change in the equipment leads to these backgrounds in the spectral resolution. On the other hand, we have the last devices in the market, such as NeoSpectra or the device of Science Technology, that shows a broad range of applicability and very good spectral resolution. However, these technical features should be tested by peer review research. If we compare the results of time with different devices, we can see that in general, for prediction of subcutaneous peak fat or the composition of ground meat, the benchtop equipment show very similar. This is one of the parameters used for tested the predictability of the equation. Sorry, and it should be higher than 2.5. As I has been saying, as we can see, the values were in general lower in the portable equipment than in the bench top equipment, but also in general enough to predict accurately the different fatty acids. The same can be seen for ground meat. However, for fresh beef meat prediction, we can see that if we compare 3 portable equipments, in this case, the results are not so good as for the previous one, but it's true that these compounds in general didn't show as well as good results as the previous one. In this case, the micronear showed the best RSQ values. Regarding technological properties, in general, the RSQ values are very low. And in this case, again, the micronear show the best results compared with, for example, Aurora. The only report I saw about this portable device didn't show a very good results for prediction of intramuscular fat. Finally, we can use these portable equipment for in situ applications such as differentiation between categories. In Spain, it's very important to make core differentiation between quality groups in the abattoir. These quality groups are defined by both the breed and the type of feeding. As we can see, the quality category can be more or less predicted in the carcass surface and in the subcutaneous fat. However, the type of feed is very well predicted in all the places, but overall in carcass surface and on subcutaneous fat. Finally, we can also use this type of portable equipment to predict the fatty acid composition with quite good RSQ values. And what about the future? The future should go towards evaluating the analytical performance of new equipment through peer review research, to specially design equipment for a specific application, and to develop new chemometric tools to develop more robust calibration and discrimination. Thank you for your attention.